Kia ora koutou, no mai, haere mai. Welcome to lesson 29 for introductory physics. In the previous lesson, we talked about electric charge and the forces on electric charge, and near the end, we defined electric potential, which is also known as voltage. And what that has set us up to do is to look at circuits in this lesson, or the flow of charge. So that's what this whole lesson will be about. Our goals are to define electric current and state its unit, explain how a voltage source such as a battery works, define resistance, both in general and as it relates to electric circuits, define direct current, and draw and interpret DC circuit diagrams. And when we do that, we want to be able to simplify those diagrams, and we also want to be able to calculate the current, the voltage, and the power relevant to different components of that circuit. So we've got a fair bit of work to do once we get to the concept of circuits. But as I said to start with, we're going to talk about what circuits are, what we mean by current, and how batteries work. So firstly, the first few parts of this lesson will be smaller, and then the very last part will be a big part where we'll do all of that circuit analysis. So the first few parts are only a few slides each. I think they'll move quite quickly. Part one is on current. We want to know what current is. What is current? We've already talked about current, we just didn't call it current. We talked about electrons moving within an object. We had the idea of two electrically conductive objects, like you get two spheres. If one of them has a charge and one of them doesn't, and then you touch them together, those electrons will flow from one sphere to the other. They will move between the two spheres. That flow of electric charge is a current. Any flow of electric charge is a current. We use the letter I, capital I, to represent current. In metals, it's always free electrons that are doing that flowing, free electrons that move. In other scenarios, you can have things which can be not electrons and that can move and cause a charge to be flowing. Remember that charge is only a property of matter. So for charge to be flowing, something has to be moving, and that something has to have a charge on it. In the case of metals and all circuits, it's electrons. It's free electrons inside the metal that can move around. They have a charge, they're moving, therefore they are a current. It is possible, although we're not going to look at it in this course, to have a current caused by other things, such as if you have an ion. Remember the idea of an ion, an atom that's gained or lost an electron, and it's in a solution. So you might put some sodium ions in a solution of water. Those sodium ions are now free to move. So you can actually use those sodium ions to carry a current through that liquid water, right? And water itself is actually polar, if you remember the idea of something being polar, and that can exhibit a current as well. And so that's why water is dangerous around electronic circuits. You may also remember way back when we were talking about the states of matter, we mentioned the idea of a plasma. A plasma, we said, was an ionized gas, which is atoms with the electrons stripped off it, and you've got these ion atoms, and you've got these negatively charged electrons, and they're all just in a gas, and they're all free to move around. And so plasma was a different state of matter from a regular gas, because it was this electrically conductive gas, which is a unique type of state. So that's all current is. Current is the flow of charge, and obviously charge is always part of some kind of matter, usually electrons. Technically, when we speak of current, we're talking about a flow of any charges, not just electrons. Most of the time we are just talking about electrons, but there's a complication that this brings up, right? So technically current means a flow of charge. We are normally talking about electrons, but electrons are negative. And when we're talking about current, we're talking about the way a positive charge would be traveling. Right? And so electrons are going to be traveling the opposite direction. So that means whenever you have a circuit, whenever you have something that has current flowing through it, this is a crude circuit diagram. We'll learn more about these in the later half of this lesson, as I said. But if you were to draw on the direction of the current, right, the current is the way a positive charge would go, and positive travels away from positive. It's repelled, so it leaves the positive end of the battery, travels through your circuit, and arrives at the negative end of the battery. That's the way a positive charge would go, but we're dealing with electrons, not positive charges. So electrons are going to be repelled by the negative end of the battery, travel through the circuit, and arrive at the positive end of the battery. We still always talk about current as being the way the conventional current travels. I know it seems confusing, and given every single circuit in the world operates by electrons flowing through it, it seems very odd to have this convention where the direction of the current that we talk about is opposite to the actual direction that we know the things that are causing the current are flowing. But as I said, that's because the electrons are negative, and this whole convention of electrons being negative, protons being positive was made up before we understood what was really going on in electrical circuits, and formalizing the equations around that. So it's just something that you have to learn and you have to get used to, but it should hopefully be pretty straightforward. If you remember that the current is the way a positive charge would travel, and then remember that electrons are the things that are actually traveling, they're going to be going in the opposite direction. As with any quantity, we need units in order for our measurements to make any sense. The unit for current is the ampere, A-M-P-E-R-E. And we often write that just as amps because ampere is a bit of a mouthful. Well, it's not really, but we just shorten it to amps. And we use the capital letter A for the units. So current has the letter capital I, and the units for current are amperes, which have the letter capital A. When we speak of current, when we talk about the current, we are talking about the amount of charge passing a specific point in a certain amount of time. Remember that current is the idea of charge flowing. If you want to measure how much charge flows through some wire or some component of a circuit, then what you want to know is how much charge is going past one specific point. Right? So there might be an electron goes past. Every time an electron goes past, you count that charge of the electron. So the number of electrons that go past in a second will tell you how many coulombs, remember the charge is counted in coulombs, how many coulombs are going past every second. That's all a current is. A current is just how many coulombs are going past every second. And so we use that definition. 1 ampere is a charge of 1 coulomb per second. Keeping everything nice and simple, 1 ampere is 1 coulomb per second. So if you've got more than 1 amp, you've got more than 1 coulomb per second. And likewise, less than is less than 1 coulomb per second. Now that we understand how to define current, let's talk about batteries, the things that cause current in our circuit. We all know that you put a battery in and that causes the electricity in a circuit to go, but how do batteries actually cause that? We've actually already talked about this idea as well. We talked about the idea that if you have a charged sphere and a neutral one, or even better, a positively charged and a negatively charged, then the charge, the electrons on that negative sphere are really going to want to get to the positive sphere. Or remember that conventional current is the opposite. So positive charge would want to move from the positive sphere to the negative one. In reality, we know that's not going to happen. We know negative charges are doing the moving, not the positive. But our conventional current would be from the positive sphere to the negative sphere. So a voltage source is anything that creates this kind of potential difference, this kind of electric potential energy, right, that's been stored between two different locations. Remember the idea of a capacitor. You pull electrons off one plate, put them onto another, you're left with a positive plate and a negative plate, and that takes a lot of work because the more electrons you pull off, the more you're pulling a negative thing away from a positive thing, the harder that gets, the more work it takes. And same thing for putting them back on. You're putting electrons onto a negative thing, more electrons are already on there, the harder it gets, the more work you need to keep doing that. And that's what you need to do if you were to get two spheres, the same as if you had those two plates. You're pulling electrons off one, putting them onto the other. That takes a lot of work. So you're building up all this electric potential energy. That electric potential energy, if you divide it by the amount of charge, remember that tells us the electric potential or voltage. So that's all the voltage of a battery is. It's telling you how much electric potential energy has been stored on the two ends of that battery, because the two ends of that battery are just like those two plates of the capacitor, or like our two spheres that we've got here. So that's all voltage is, how much electric potential energy has been stored per unit charge. If you have a large positive charge on one sphere and a large negative charge on the other, you have a large voltage. The bigger those charges are, the bigger that voltage is. Right? The bigger the charges, the total charge on that isolated metal sphere, the bigger that voltage is going to be. You do not need a circuit to have a voltage or electric potential. Remember that an electric potential is just the energy, the electric potential energy per unit charge. So just like we've talked about with the capacitor or these spheres here, if you go and shove a whole bunch of electrons onto one sphere, you've created a whole bunch of electric potential energy. You've used your work pushing the electrons onto the sphere to store that energy as electric potential energy. So you have a voltage. You don't need a circuit. Remember that voltage or electric potential is just a measure of the electric potential energy stored in that object, right? So you do not need a circuit to have a voltage. A battery that says 6 volts on it, that is 6 volts regardless of whether it's connected to a circuit or not. So anything which would cause a charged particle to experience a force is creating a voltage. It's that simple. If you have something which would cause a charged particle to experience a force, then you are creating voltage. And that means if you have anything that has a charge on it itself, because as we know, that's what causes other charged particles to experience as a force. If you then connect your two spheres, you've got one big positive one, one big negative one, and you connect them with a metal wire, you'll get a sudden rush of electrons moving from the negative sphere to the positive sphere. That should be pretty common sense. If you connect them, it's the same as touching them, right? If you touch them, a whole bunch of electrons will flow through. If you connect them with a little conducting wire instead, same deal, you're going to get a bunch of electrons that flow from the negative one to the positive one. So our electrons flow from negative to positive. Remember, that means the conventional current is the other way. It's the way a positive charge would go if there were positive charges, and that would go from the positive sphere to the negative sphere. However, the electrons move pretty quickly. They move pretty quickly, and that reduces the charge on the negative sphere and increases the charge, also reduces the charge on the positive sphere, increases the number of electrons. So you're getting both of these spheres approaching neutral, or at least approaching the same charge as each other. So as the electrons move, the more the electrons move, the lower that voltage gets. Eventually, there'll be no voltage because the two spheres will be at the same charge, and there'll be no need for the electrons to move. If the negative and positive spheres started at equal and opposite charge values, then they would all become neutral and all become zero charge over the whole system. If they started at different magnitudes, then you would end up at this equilibrium that's not perfectly neutral. But you would end up, regardless, at a point where the two spheres had the same charge, and so there's no voltage between them. No need for a charge to move from one to the other. So anything that has a charge can create a voltage. It does create a voltage, but it's not always going to be a good voltage source. It's not a reliable source if it just disappears really quickly, like those two metal spheres. So a good voltage source is something which will cause a continuous current, not just a brief surge like we saw with the two charged spheres. If you connect the two charged spheres, a bunch of electrons move, and pretty quickly they're all at the same charge, nothing else is happening. So that current was a real quick little burst and then drops to zero pretty quickly. We drop to no current. So a good voltage source, what they do is they actually store some other kind of energy inside them, which they then convert to electric potential energy as required. Batteries use chemical potential energy. So they've got a whole bunch of chemicals inside them that can undergo chemical reactions and convert their chemical potential energy into electrical potential energy, which can then be used by the circuit. Generators use kinetic energy. So generators, you might have a water wheel in a river, or you may have something that's being powered by a petrol engine, and it uses, whatever it uses, it causes kinetic motion, right? Kinetic is just motion, kinetic energy, motion energy. So something is moving, and then it uses that energy, that kinetic energy, to convert into electric potential energy and cause a voltage. So that's what generators do. So there's different ways you can get a good voltage source. We're going to talk about batteries a bit more. So a good voltage source providing a current is going to be one, imagine those two metal spheres again, right? But now imagine that they are at the ends of a battery. Right? Those two metal spheres are now at each end of a battery, and inside this battery, you've got this chemical process, and the electrons, when you connect the two ends of the battery, will flow from the negative end to the positive end through that wire. That's what a battery does. The electrons are repelled by the negative end, they will escape, go through the wire, and end up at the positive end of the battery. Once they get to the positive end, if they just stayed there, then that end is now less positive and the electron end is now less negative, and you lower your voltage, you lower your current as a result. And that's not what we want to happen. So what the batteries do instead is they have a chemical process, which as soon as an electron comes into that positive end, it takes the electron off the positive end, uses it in a chemical process, which spits an electron back out to the negative end. Right? So they use a chemical process to basically just take the electrons off the positive end as they arrive and do stuff to them and end up kicking a different electron back out the other end onto the negative end. So that's what batteries do. That's all they do. A battery has a whole bunch of electrons on one end, a whole bunch of missing electrons on the other, so a positive charge, and a chemical process occurring inside, which keeps that state in as the system for the battery, right? Keeps the system in that state, I should say. So whenever an electron arrives at the positive end, gets sucked in through the chemical processes, and one gets spat out onto the negative end. So keep the negative end negative and the positive end positive. That is all a battery is doing. If you study chemistry, you may learn more about that chemical process. As physicists, we're not too worried about that chemical process. You can certainly go and investigate it and research if you are interested, and it is interesting, but I'm not going to go into it. The batteries just does that. We won't say by magic, but it does it by chemistry, which if we don't understand chemistry may as well be magic, right? So it's electrons getting sucked off the positive end, process, and then pushed out onto the negative end. And that will keep that current flowing, because as long as that negative end is always negative, then electrons are always going to want to flow through that circuit towards the positive end, because that's what a positive negative voltage difference is going to do. It's going to cause those electrons to want to escape the negative end and to be attracted to the positive end. So now we can talk about what a circuit is. This isn't the last section, last part of the lesson where we're going to talk about circuit diagrams and analyzing them. This is just the definitions of a circuit. Whenever we connect the two ends of a voltage source with conductive material and provide a path for the current, we have created a circuit. That's all a circuit means. A circuit is a pathway for electrons to travel from the negative end of a voltage source to the positive end of a voltage source. That's it. Generally, you're going to go and put components and other things in the way, and you're going to use the energy of that battery to power those components. But regardless, even if it was just a piece of wire, then you have a circuit. Remember that voltage is the term for the difference in electric potential electric potential energy between the two ends of the voltage source. So voltage is not something that flows in the circuit. Current flows, charges flow, but voltage is just a measure of the difference in charge between the two ends of the battery, the thing that causes the current and causes the electrons to flow. So voltage does not flow through a circuit, it's applied to a circuit, because we go and we put the battery in the circuit. You now have one end of the circuit having a big negative charge, the other end having a big positive charge. So electrons are going to be pushed away from the negative end and pulled towards the positive end. So voltage is applied to or across a circuit. Whenever the electrons are flowing in a single direction, as per all our examples so far, we've had a negative end and a positive end. The electrons always will flow away from the negative end and towards the positive end. That's called a direct current, because the flow, the direction of the electrons, and therefore the direction of the conventional current, which would be the opposite to the direction of the electrons, that direction never changes. Batteries are always direct current, because the way batteries are set up is to have a negative end and a positive end. And so electrons will always flow a very specific way. They will always flow from the negative end to the positive end. So batteries always produce a direct current. When an electron leaves a battery terminal, though, it does not just zip around in an instant and end up back in the other terminal really quickly. So it doesn't leave the negative end, zip through the circuit and end up back at the positive end, because the wire that makes up the circuit is already full of electrons. It is a metal, it has all these free electrons, it's already full of electrons. What happens is that if one electron leaves the negative end of the battery, if it jumps off into the wire, all that does is it pushes every single electron in that battery all the way around the circuit along one electron space. Right? Obviously, the electrons aren't stationary, they're in a sea, they're all flowing and moving, kind of like water, but a sea made out of electrons. But if you push one extra electron in, then it just sort of shoves them all along very slightly all the way through that metal circuit until you get to the positive end, where one electron at that end of the wire will be pushed off the wire and into the positive end of the battery. So the electrons don't just zip around, right? There's like this big queue, this huge big queue of electrons in the wire, and you push one into the wire off the negative end of the battery, and that just means that one at the other end will come off the wire and into the positive end of the battery. So they are different electrons, right? It's not one electron leaving the negative end, zipping around at the speed of light and jumping into the positive end. That doesn't happen. They actually move quite slowly. So it's this big queue. Remember, electrons are free to move around within the metal, so they're sort of flowing all the time anyway. But when we talk about the movement of an electron in a circuit, we're talking about the extra movement that it has because of this electron that we're pushing in, and that's really slow. It's about 1/10 of a millimeter every second, so it's not fast at all. So these electrons are just very slowly moving around this circuit once you connect to the circuit. But remember that electrons are really tiny, so we've got heaps of them. So even in a really tiny, thin diameter wire, the cross section, if you cut through the wire, the cross section, there are heaps of electrons that are coming past that point every second. So even though you have really slow moving electrons, you have so many of them that you still get significant total numbers of Coulomb going past every second, which is what our current is. Next part is resistance. So we've got this idea that a battery, or a good voltage source of any kind, but we're going to stick with batteries mostly. We've got this idea that a good voltage source will cause a current. That current is the movement of electrons as they leave the negative end of the battery, flow through the circuit, and arrive at the positive end of the battery. Resistance is any kind of force which opposes the electrons traveling through the circuit. That's all resistance means. It's resistance. It's the same uses of the word resistance that you would use in general. Resistance is just something opposing something else. In this case, the resistance of a circuit is any force that opposes the electrons traveling through the circuit. If the electrons were leaving the negative terminal because they're repelled by all the other electrons on the negative terminal, and there was no resistance at all in the wire, then the electrons would go really quickly. They'd accelerate heaps because there's this big force pushing them away. We'd get a really high current. We'd get heaps of electrons leaving really quickly. But in reality, the electrons are trying to move through a piece of metal, and that metal is made up of atoms, and these atoms have thermal energy, and you remember thermal energy means things are jiggling around. So you've got all these atoms which are sort of vibrating on the spot, jiggling in their little location within the metal crystal, and the electrons have to try and get past that. So just the simple fact that they have to travel through a metal is already providing resistance. Different metals will provide different amounts of resistance, but every metal does provide some resistance, unless you've theoretically gotten down to absolute zero so that the atoms sat perfectly still, weren't moving at all, then the electrons would have no trouble getting past because the atoms aren't sort of bouncing around in their way, right? So any kind of wire, any material, whatever the material is that the circuit is made of, will provide some resistance. That happens. The amount of resistance it provides varies, though, depending on all sorts of things, such as what type of metal you've got, how big the cross-sectional area is. You can imagine if you have a tiny little wire connecting the two ends of a battery, then that's a really little path, and that electron doesn't have a lot of choices in how to try and get through it. So it's going to be quite hard because it can't just go off over this side. It's got to stay within this little section of wire. If you've got a really big fat wire, then the electron's got heaps of possible locations, and also heaps of electrons can go at once. So you get more electrons traveling through. So it's going to have a lower resistance. It's easier for the electrons to get through. So it depends on all sorts of stuff, the physical size of the wire, as well as what the wire is made of. Hopefully, as you can figure by thinking about that voltage, that current, and that resistance, if you get a bigger resistance, more opposition to the electrons flowing, then that means that you're going to get less electrons flowing, and so you're going to get a lower current for the same voltage. So if you keep the same voltage, but you provide more resistance, you try and stop the electrons flowing a bit more, then you'll get a bit less flow, so you'll get a bit less current. And that's what Ohm's law is. Ohm's law just says that the current is proportional to the voltage and inversely proportional to the resistance. I is equal to V over R. I didn't actually mention that on this slide. Resistance, we use the letter R to represent resistance. And the units, I'm assuming I've got on the next slide there, ohms, which we'll look at in a second. We can rearrange this Ohm's law to V equals IR or R equals V over I. It's useful to remember all three, but if you just choose one of them to memorize, then you can rearrange it to get the other two. You will need to use it in all formats. So do remember Ohm's law. So as I said, if you have a voltage source, then it will produce a current, but the amount of current it produces is determined by the resistance of the circuit, of the whole pathway from the negative end to the positive end of the battery. The units for resistance are ohms, named after the same guy that Ohm's law was named after, obviously. The symbol is another Greek letter, and this one is an omega, and it's sort of awkward to draw. So have a practice at drawing that. It's just sort of a little, not quite a full circle with a couple of lines out the side. I'm not particular about how you draw it. You don't have to draw it perfectly, but do try and make it clear that it's an omega, that it's resistance when you do it. If you really struggle, you can just write ohms in full, but it is better to practice using this symbol. But I'll jump over the document camera and I'll show you how I draw it and also the different options you have. So when I draw it, I tend to just do this, right? So it's not pretty, but it's pretty obviously in ohms, right? You can also, if you want, you can draw the circle and then just do little feet on it. That's pretty common to draw a sort of a circle, little feet. Some people do it more angular, as I started to do there. They'll sort of go like that. I don't recommend doing a full angular, triangular shape like that. But even if it ends up sort of pointy, but not complete points, it's pretty obvious that's an ohm and not going to be something else. So as I said, I'm not too worried, but you certainly don't have to try and do the little fancy little feet and then curve it up and around and do anything like that, right? You don't need to do anything fancy, just as long as it's obviously an ohm is fine. We define the amp as 1 coulomb per second, and in the same sort of idea, we're going to define the ohm as the resistance required for 1 voltage, 1 volt, to create a current of 1 amp. So that's the definition. So we have all these things that are defined based on one of something else. So 1 amp is 1 coulomb per 1 second. 1 ohm is the resistance needed for 1 volt to produce a current of 1 amp. So all these different ones. Sometimes we want to deliberately increase the resistance of a circuit. The reason we would want to do that is to control the magnitude of the resultant current flow. So if we don't want heaps of electrons flowing through our circuit, we'll chuck a bunch of resistance into our circuit to try and slow it down, right? And cause that electric current to slow down, to decrease. To do this, we use components called resistors, and there's a photograph of a resistor right there. It's a pretty common little shape, little item. Most people have seen them. Resistors don't have a direction. It doesn't matter which way the electrons are trying to go through it. They're going to get opposition either way. If you try and put an electron from the bottom, send it up through this resistor, that resistor is going to oppose that motion. Same thing if you put one on the top and try and send it downwards through the resistor, it's going to oppose it. Same deal. What resistors do is convert electric potential energy into heat, but they have special insulative materials wrapped around them to try and not actually cause a whole bunch of release of heat all at once that will damage anything else. But that is essentially what they're doing. They are taking that electric potential energy that the electrons are being pushed away with, and they convert it into heat. Right? So it's a good idea to remember that the whole reason the electron is moving through the circuit at all is because it's being pushed by the charges on the battery. Right? The charges at each end of the battery are pushing that electron through the circuit. Right? And so the electron is being pushed through the circuit. If there's a resistor, it'll be pushed through the resistor. As it's pushed through the resistor, we now have something doing a force, right? Applying a force to something as it travels a distance. It is the electron traveling through the resistor. That means it's doing work. That work is exactly the same idea as if you push a box along some carpet. You are providing the energy, you're providing the force, right? You are providing the work to the box. The box travels along the carpet, converting that work that you provide into heat through that friction, also into sound and a bit of deformation. But it is converting that energy you provide and losing it due to friction. Exactly the same idea. The battery is providing the force to the electron. So it is pushing the electron. It's doing it from a distance, right? Not like we push a box by direct contact. It's doing it by distance because it's electric charge. It repels from a distance, but it is pushing that electron. The battery is pushing the electron through the resistor. As it does so, that resistor is kind of like the carpet. It's the friction. And that resistor takes that work being done on the electron and dissipates it so that that electron is losing energy. If there was no resistance, then any force that is being done, any work that's being done on that electron would be accelerating it, right? Just like if there was no resistance for the box and you push it, you're accelerating it, you're giving it kinetic energy. So that would happen to the electron if there was nothing in its way, and it would get really fast. And that's what we talk about. The current will get really high because it's just all becoming kinetic energy, and the electrons wouldn't be traveling that really slow speed anymore. They'd accelerate and end up going really fast through the circuit. You'd get a really big current. So I've probably over-explained this idea of what resistance is, but as I said, the idea in this first half of this lesson is to really understand what's going on in a circuit. Because if you really understand all of this, if you really understand why circuits work, it makes analyzing them so much easier, right? Finally, before we get to analyzing circuits, we want to understand power. Power is the same definition as we've met before. An electron leaving the negative terminal does so because it has electrical potential energy. By the time as it is received into the positive terminal, it has no electrical potential energy. If there was no resistance along the way, as we said, that would have been accelerated, it would have turned into kinetic energy. And then when it hits the positive terminal, that energy would be dissipated through the collision. It would get dissipated as heat then, but generally it'll be dissipated along the way, going through the wire, because there is resistance, so there is friction to overcome. So the energy gets dissipated along the way. By the time it gets to the positive terminal, it's got no kinetic energy, because remember, it's going really slowly. Right? It always goes slowly through any real circuit. Right? There's always enough resistance that it will be slow. So it's got no real kinetic energy, but it's now got no electric potential energy because it's at the positive terminal, and that's where it wants to be. It can't get any closer than being on the positive terminal. So all that energy has been used up. The electric potential energy that the electron had at the negative terminal, the one that caused it to be pushed away from the negative terminal, has been used up. Right? It has done work as it went around the circuit. It has done work. That means it has used up its energy. That energy has been converted into different forms. If it was just resistors, it's been turned into heat, but it may have also been turned into mechanical energy. If we had a little motor that was attached to the circuit, it may have been turned into light if we had a light bulb. Right? So whatever the component is, electric components that go in circuits, other than resistors, are things like light bulbs and motors. And so all they are set up to do is take electric potential energy and turn them into some other form of energy. And so that's what's happening. The electron starts with a bunch of electric potential energy, travels through the circuit, and uses up that energy as it goes. And by the time it gets to the end, it's got no energy of any kind left because it's at the positive terminal and it's got no kinetic energy and it's already done a bunch of work. So the rate at which that electric energy is turned into other forms of energy is the power of the circuit, sometimes called electric power, but really it's just exactly the same. It's power. It's the rate of work per second, right? So work per second is just our same definition of power, but now we're talking about work done due to an electric potential energy that an electron had to start with. To calculate power, you need to know how much electrical potential energy each electron has converted into other forms of energy and how many electrons have done this. Right? So each electron has some electric potential energy at the start, and it uses it up as it goes through, and we need to know how much energy that was, how much energy did it have that it used up, and how many electrons did that every second. Right? Because it's not just one electron traveling through our circuit, it's a constant stream of them. That's what direct current means. That's what a good voltage source will produce, is just this constant stream of electrons going through your circuit, all being used to convert electric potential energy into other forms of energy. So the power is based on that. So we already saw voltage being how much electric potential the electrons have per unit charge. And we already saw current being how many electrons are going past every second. So we've already got the information we need. We've already got how much electric potential energy there is in the circuit or due to the battery, and we've got how many electrons are traveling past every second in the circuit. So power is just the product of those two. It's voltage times current. Voltage is how much electric potential energy there is per unit charge, and the current is how many units of charge are passing every second. All right, so simple formula there. We've already met power, as I said, exactly the same, so the units are the same. The units for power are still watts. We still have a capital W, exactly the same. And just to check everything makes sense, remember that the voltage is the energy per unit charge. The current is the charge per unit time. So if we multiply them, we get energy per unit time, which is exactly what we expect for power. So everything is still just as we had it before. It all hopefully makes sense. As I said, we have light bulbs in a circuit which convert electric potential energy into light. Right, so rather than heat with a resistor, we can turn it into light using a light bulb. Light bulbs, when I talk about incandescent light bulbs, I'm talking about the old style light bulb, the ones with the little filament. So not an LED, not a modern kind of lighting source, but an old style incandescent bulb with an actual little filament inside a little glass bubble. Right? Those style of light bulbs, they are very useful because the greater the power being used by the bulb, the greater the energy per second being converted by the bulb into light, the brighter the bulb will look. And so you can use a light bulb as a very simple visual gauge of how much power is being used. If you have two identical light bulbs and one is shining brighter than the other, that means that that light bulb is using more energy per second than the one that's a bit dimmer. And so light bulbs are this great tool for us to put into two identical circuits and see which one has more power, which one is using more power. So standard light bulbs, just like a resistor, they don't have a direction. Doesn't matter which way the electrons go through the light bulb, it will convert it into visible light. And the more energy a light bulb produces, the more energy a light bulb uses, the more light it will produce each second and therefore appear brighter. They are essentially turning energy into visible light, but they also turn some into heat, as you will be aware if you've ever used any of these old school incandescent light bulbs. So not the halogen or the LED ones, but the old school with a filament. They will produce quite a lot of heat as well, but regardless, they still produce visible light proportional to how much power they are using. So that's the first half of the lesson done. I say half, it doesn't mean exactly half of the time. I don't know how long this is going to be as a lecture, but the first half was all about the ideas, the theory behind circuits, right? So what causes the current, what is current, how do we define it, how do we define resistance and power and all of that. Now that we hopefully understand all of that and we have this mental picture of what's going on inside a circuit at that atomic level with the little electrons being repelled by the negative terminal of the battery because it's just full of so many negative electrons that they're all repelling, and so they all try and escape into the circuit because you give them this pathway that they can travel along. And then they use their electric potential energy. They're being pushed by the battery, and they use that energy, the push, the work that's being done on them, they use that to convert into other forms of energy as they go around the circuit. If you can remember all of that, then analyzing the circuits will hopefully make quite a lot of sense. It won't be super confusing. One of my little pet gripes around how circuits and electricity and electronics is taught, not just in schools, but often in universities, is that they don't really spend much time building up that stuff that we've just talked about, the first half of this lesson. They don't really talk about that. They just go straight into your formulas, your Ohm's law, draw your circuit diagram, calculate these. And so students get these formulas, and so they have the tools to analyze the circuit. But just like way back in my intro video where I showed you a problem and I said, you can follow this problem, you can understand this problem because I've told you the equations and I've shown you the math and you know how the math works. But it's the same problem. If you don't understand that physics underlying it, you don't understand why we're using these tools, why we're using these equations, and it means that you're not really going to know how to deal with a scenario that's slightly different than one you've seen before. Right? So even if you just change something little, if you don't understand the physics, you don't understand what's going on, then it means that you're going to be trying to apply the wrong equations and not understanding why it's not working. So with all of that said, my little rant out of the way, let's have a look at some circuits. To start with, we need a way to draw circuits. We don't want to be sketching a battery and sketching a light bulb and drawing the wires connecting. We don't want to be doing that every time we want to communicate how a circuit is set up. So we've come up with these agreed upon rules for circuit diagrams. And that way we can just look at a simple diagram, and we always agree that if we see this symbol, it means a battery. If we see this symbol, it means a resistor, and so on. So we are just going to use really simple components, the simplest 4 components. That is DC voltage sources, such as batteries, resistors, light bulbs, and switches. Additionally, we're only going to connect these with wires, which are just simple straight lines on our circuit diagram. So the symbols are, a voltage source is drawn as 2 parallel lines, right? And this just represents the positive and negative ends of the battery, right? One being charged up positive, one being charged up negative, and you put it in the circuit. That's all the voltage source is, so that's what we draw it as. The positive terminal is the longer one, the shorter terminal is the negative one. The plus and minus symbols aren't part of the battery symbol, but you are allowed to draw them on if it helps you. So I've drawn them on here just to remind you the longer one is positive, the shorter one is negative, but technically they're not part of the symbol itself. Resistors, there are a few different ways to draw them. The most common two are these two, the zigzag and the rectangular box. Both are perfectly acceptable and both are fine. I will use both intermittently, interchangeably, so you are free to do that as well, or if you prefer one, just stick with it, that's fine too. Light bulbs are also very simple. It's a circle with a cross through it. Circle with a cross through it. Those lines coming out the side are just the wire from our circuit. So a circle with a cross through it is the battery. And finally, we want a switch, which is just a way to control when the circuit is on or not. We don't want to have to take the battery out and disassemble the circuit entirely to stop it flowing. So instead, by introducing a switch, it means that that current will only be able to flow. The pathway is only there when we close the switch. And that's the same with household circuits. When you've got your lights that are connected to a switch, that's so that you don't have to actually remove the light bulb just to turn it off. You don't have to go and break the circuit. You can just use the switch to stop the circuit from being completed or not. Same thing in a little DC circuit. We draw it just like that with a one section of the wire just slightly open, like a slightly open door, and that just shows that the circuit isn't completed. There's no way for that circuit, for the current to flow. Once we've got the components we want, arrange them how we want, then we just use straight lines to connect them. I do recommend getting a little ruler if you don't have one, and using a ruler for circuit diagrams. If you try and draw them by hand, they inevitably end up getting messy and it becomes difficult to interpret. And I don't really fancy marking assignments and exams where you've got messy circuit diagrams. So if they're not easy to interpret, you can draw them by hand. If you really don't have a ruler and really don't want to go and get one, you can draw them by hand, but take time to make sure you get the lines as straight as you can. Don't just sit there and do squiggles and curves and just connect the battery to the switch with any old wiggly line, right? Try and do them as though you had a ruler if you don't. Sometimes we have multiple things in a circuit. In fact, just about every time outside of really simple circuits that we're creating for the purposes of education, we just about always have multiple items in a circuit. And if those items are in a line, right, if the electron has to go through every single component, that's called a series circuit, right? It's called a series circuit because the current flows through every component one after the other in a series, right? If you imagine an electron, remember the electrons leave the negative terminal. The conventional current would be from the big positive terminal around clockwise to the negative. Our actual electron flow is from the negative terminal anti-clockwise around through the components to the positive terminal. But if you follow the path of an electron, you have to go through every component. You have to go through the resistor, you have to go through the light bulb, you have to go through the next light bulb and then through the next two resistors and get back to the start. You have to go through all of them. There's no way to avoid some of the components. Right? That is a series circuit. It has to go through every component in series. When you have multiple items in series, multiple resistors in series specifically, then you can simplify them. And simplifying them is just saying, we've got three resistors here. One of them has 5 ohms resistance, one of them has 2 ohms, and one of them has 3 ohms. Remember that the resistance is a measure of how much force is being used to oppose the electron flowing through it, essentially, right? That's essentially what resistance is. So if you've got one resistor that's providing 5 ohms of resistance, then the electron has to overcome that to get through it. And then it has to overcome another 2 ohms of resistance to get through the next one, and then another 3 ohms to get through that third one. That's exactly the same total resistance as if the electron just had to go through one 10 ohm resistor. Right? As you can think of it as climbing stairs. If you have to climb a 5-stair staircase and then a 2-stair one and then a 3-stair one, and it's 3 separate little staircases, that's the same height as if you climbed one 10-step staircase, right? So it's the same idea as resistors here. If you have to go through each of them one after the other, it's the same as just going through one that had the same total. So that's all you have to do. And the reason we simplify resistors will become clear as we move along. But for now, just remember that that's all you have to do. If they're in series, add them up, easy. So if you had a circuit that had those 3 resistors, you could take those 3 resistors out and put a single 10 ohm resistor in, and the circuit would behave identically. It would behave exactly the same as it did with those 3 resistors. And by behave, I mean it would have the same current and the same power usage as it would for having the 3 resistors. When we have light bulbs, remember that a light bulb is just converting a bit of electrical potential energy into light as well as heat. A resistor is turning it all into heat. So when we have a light bulb, we can treat them exactly the same as we do as a resistor for the purposes of simplifying. So that means if an electron has to go through a 5 ohm resistor and then an 8 ohm light bulb, the amount of resistance that it's encountered, even though it was for a resistor and then a light bulb, it's the same total resistance as if it had to go through a 13 ohm resistor. So when we're simplifying, as I said, the reason we simplify will become clear. When we're simplifying, we can treat light bulbs like resistors and we can just add up those resistances. So a 5 ohm and an 8 ohm, doesn't matter if they're resistors or light bulbs, they'll become a 13 ohm resistor when we simplify. When we have current in a series circuit, there is only one path. That current is the same everywhere. It doesn't matter where you look on that circuit. If you look at straight outside of the negative terminal, or you choose a position anywhere around the circuit, or you look just near the positive terminal, the number of electrons going past every second is the same no matter where you look. It has to be, because remember, the electrons are like a big queue, and if one leaves the negative terminal, it pushes them all along one. So that means if one changes here, then you've got one moving here, and you've got one moving here, and one moving everywhere. And so the number of electrons going past every second at any location must be the same. If it wasn't, then the circuit wouldn't make any sense, because you'd have a whole bunch of electrons, say you had a whole bunch of electrons leaving the negative terminal, but you had no current at the positive terminal, so the electrons weren't getting into the positive terminal. Then that means they must be piling up somewhere in the circuit, and that doesn't make any sense either, because you're going to be creating this big pocket of negative charge. But a big pocket of negative charge is like the negative terminal of a battery. It takes a lot of energy, a lot of work to build that up. So it doesn't make any sense to have that. So what we get is that the current, the number of electrons passing every second, is the same everywhere in a series circuit. The voltage in a series circuit, though, remember the voltage. The way to think of the voltage is essentially the amount of energy the electron has as it leaves the battery, as it leaves the negative terminal, is the amount it has to use up as it travels around the circuit. And so it's basically got this little store of energy. It's like, I know some people use an analogy of having like a wallet full of money, and you've got to use all that money up before you get back to the positive terminal, and you spend it at each different component in the circuit. But I'm not a big fan of that analogy, because hopefully by this point you understand exactly what's going on in the circuit. So we don't need analogies. Analogies are when you don't fully understand the subject matter. If you fully understand the idea of the electron having some energy because it's being pushed away by the negative terminal of the battery, then it's got that energy to use up, and it can't have any left when it gets to the positive terminal. And so it has to use that energy on each component. And it uses that energy to overcome that resistance of each component. The bigger the resistance, the more energy it will need to overcome it. And so the energy will go into those different components as the electron travels through the circuit. Because we deal with conventional current, we always write this the other way around. I apologize. I know it's confusing, but it's just the convention, and it's something that you need to get used to. If you prefer to think of it the other way, you can what you can think of it is the electron leaves the negative terminal and it's spent 0 volts of energy. So rather than thinking of it as having 6 volts as it leaves the positive and spending it across each component, you can think of it as the electron having spent 0, and it must have spent all 6 by the time it gets to the positive terminal. Exactly the same idea, and it will result in the same numbers. So conventional current wise, we start with 6 volts at the positive terminal. We've still got 6 volts here, because even though I said that all wire does have some resistance, the resistance in a wire is so low compared to actual resistors and light bulbs that it's pretty much negligible. Remember the idea of negligible, it means it's below our precision. We don't care about it. It's there, we know it's there, but we don't care about it because it's so small. So the amount of energy the electron actually needs to travel through this little bit of wire is practically nothing compared to the amount it's going to need to get through this whole big resistor. So we say that it hasn't really used any of its energy traveling just through that bit of wire. Then we've got 2 identical resistors. It must be going to use half of its energy in each. There's literally no reason for it to use different amounts of energy in each one if the 2 resistors are identical. And that's exactly what happens, right? The bigger the resistor, the more energy it will use going through that component. So that means if it's got 6 volts, as it gets to this first component, it will use 3 of it, half of it, going through that first one. It'll then lose nothing as it travels through that little bit of wire, negligible, so nothing, and then use the other 3 volts as it travels through this resistor. And so our conventional current pathway, we've now used up all of our voltage, all of our electric potential, and we have nothing left, and we just travel through the wire back to the negative terminal, and we arrive with no voltage left. As I said, electron just does the opposite. So that was our conventional current direction. In the real, what's actually happening, we have an electron that's leaving, and it's at the moment it's spent 0 volts, right? It's spent nothing, it's used none of its energy. The wire, as we said, is negligible, so it arrives at the bottom of the first resistor with having spent no volts. It then spends half of it going through the first resistor, half of it going through the next resistor, and then it's spent all 6, and it gets back to the positive terminal having spent it all. That's the idea of voltage. Right? The idea of voltage is just how much energy we've got that this electron can use, and it has to use it all, and it'll use it on whatever's there. If there's a single component, it'll use all of it. If we've got a 6-volt battery, a single component, then every single electron that travels through that circuit will use all 6 volts in that one component. Right? That's just what it does. If you've got 2 identical components, then it'll use the same amount of energy, exactly half in each component. If you have 2 different components, then it'll use the amount of energy in proportion to how big the resistors are. If this resistor is twice as big as this one, it'll use twice as much energy in the one that's twice as much resistance. Right? So that would have twice as much of a voltage drop. So the way we talk about it is voltage drop, and voltage drop is literally saying how much of that voltage has been used for the electron to travel across that resistor. In the case of the example here with 2 identical resistors, the voltage drop across each is identical. In the case of 2 different resistors, they would have different voltage drops. The voltage drop must always add up to the voltage provided by the battery, because remember that voltage drop is just a way of saying how much energy is used across that component for the electron to travel through it. And the amount of energy it uses to travel through it must be, in total across the whole circuit, the same as the amount of energy it starts with, given to it by the battery charge, right? By the fact that battery has that potential voltage difference. Hopefully that'll make sense. That is what voltage means in a series circuit. Right? The amount of voltage used across each component, the amount of energy needed by the electron to get through it. The other type of circuit that we're going to concern ourselves with is the parallel circuit. So in the series circuit, the electron had to go through every single component. In a parallel circuit, it can only go through one branch of the circuit. It can't go through all of them. So here, if you have an electron, then it would travel off this negative terminal down to the bottom. It would go along, and then it can either go up through the first component, or up through the second component, or up through the third component, and then go back to the positive terminal. So it doesn't matter specifically which one it goes through. Right? The amount, we'll talk a bit more about which one it decides to go through, but it doesn't matter specifically which one it goes through. The point is it only goes through one of them. It can only go through one of them. It can't, once it gets through one of them, then go back through another one, because that would be traveling back towards the negative terminal of the battery. And it can't do that because it's being repelled by the negative terminal. That's why it is moving around the circuit at all. It'd be like pushing a box and then the box suddenly goes back towards you. Right? It doesn't make any sense. And it's the same thing here. Electron traveling back towards the negative terminal doesn't make any sense. The negative terminal is the thing that's pushing it away. So the electron can only travel through a single branch of this parallel circuit. That's how we know it's parallel. It can travel through one branch of the circuit. When you've got resistors in parallel, it's a little bit more complicated. In series, we saw that we could just add them together. In parallel, it's kind of the opposite of that. You add the reciprocals of the resistances. Remember that the resistance tells you how many electrons can go through the circuit at once. If you have a lower resistor, then you're letting more electrons through. But if you instead put a second identical resistor parallel to that first one, now you've got 2 pathways for the electrons. And that means that you can let twice as many electrons through. So when you have parallel resistors, you're actually lowering the total resistance because you're letting more electrons through the circuit. You can imagine that like having 2 doors. If you've got 2 doors and you've got a bunch of people that want to get from one room to the other, and you only open one door, then a certain number of people per second can get through that door. But if you open both doors, twice as many people can get through the doors, right? Same thing here. You've got a resistor, electrons going through the resistor, then there'll be a certain number per second going through that resistor around the circuit. If you put a second identical resistor in parallel with it, so the electrons only go through one or the other, each of those resistors is going to let through as many electrons as the other one does, and you've now got twice as much current. And so if you can agree with that, if you follow that reasoning, then the maths to prove the reciprocal law formula is a little bit more complicated. It's not terribly complicated, but it's not part of this course, so I'm not going to include it. All I want you to do is remember this formula. The total equivalent resistance is equal to the reciprocal of the sum of the reciprocals of all the individual resistors. So it's a little bit complicated to say it out loud, but it looks like is written here. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over all the different Rs, 1 over each R all the way through all the resistors. In this case, we've got 3 resistors, a 5, a 5, and a 10. So our 1 over R total is going to be 1 over 5 plus 1 over 5 plus 1 over 10, which is 1 over 2. But remember that we've got 1 over R total. And I really want to emphasize this point because this is the most common mistake when converting resistors in parallel, when simplifying circuits with resistors in parallel, is that you get to this point and you forget that you've got 1 over R total is equal to 1 over 2. Right? And people just go, right, well, that's the same as a half ohm resistor. It's not. 1 over R total is equal to 1 over 2. So R total is equal to 1 over a half, or 2. Right? So the equivalent total resistance here, 5, 5, and 10, equivalent total resistance is 2 ohms. So that last step to take the inverse, the reciprocal of that result. 1 over R total is equal to a half, so R total is equal to 1 over a half. So do remember that final step, please. It's a very easy mistake to make. So what you can see is that by adding more resistors, we had a 5 ohm, we add another 5, and then we add a 10, we've actually lowered the total resistance. We've gone down to 2 ohms total resistance. And that's because each of these pathways lets through some electrons. So in order to have a single pathway that lets through just as many electrons, it needs to be lower resistance. Current in a parallel circuit can now travel along different paths. Remember that the current is how many electrons are going past every second. So that means that the number of electrons going down each path is now longer not necessarily the same everywhere. Well, it won't be the same everywhere. Remember, in a series circuit, the number of electrons everywhere was always the same because there was only one path. In a parallel circuit, the total number of electrons coming off the negative terminal every second, right, is getting split up into the different pathways. So you're not going to have that same current down each pathway. You're going to have a fraction of that current. If there were 2 identical pathways, then you would get exactly half the current down each pathway. But if you've got 2 different pathways, then you're going to get different currents. If you've got 3 pathways, you're going to get 3 different currents, or potentially 3 identical currents if they're all identical pathways. So you're going to get different currents down each pathway. The total current, the total number of electrons going past each second across all 3 pathways must be the same as the number of electrons coming off the negative terminal every second, because the electrons, you can't add or you can't create or destroy the electrons in the middle of a circuit. So the number leaving the negative terminal must be the same as the total number going down all 3 pathways added together, right? And the pathway that has more resistance will have less electrons going down it. More of the electrons are going to go down the one that's easier to go down. So if we go back a slide to look at this 5, 5, and 10, right, these 5 ohm ones, they're a bit less resistance. More electrons are going to go down those pathways than are going to go down this 10 ohm one, because 10 ohms is more resistance. So you're going to get twice as many electrons going through the 5 ohm resistors as you are going to get going through the 10 ohm resistor. So a path with more resistance will have less current than a parallel path with less resistance. There will still be the whole circuit current, but it will then split every time the circuit splits into different branches. And this, I've already made this point, but the sum of the current in parallel branches of a circuit must be equal to the total circuit current. As I said, if you understand that current is just the number of electrons going past every second, this should make perfect sense, because you can't have 10 electrons coming into a circuit and then only have 2 down this branch and 2 down this branch, because that's only 4. So if you've got 10 coming into the circuit and then only 4 going down the 2 branches, what's happened to the other 6, right? It makes no sense. They have to be accounted for. So instead, what you would have if you had 10 coming off the negative terminal and then 2 identical branches, you'd get 5 going down each branch. Then they would join up again when the branches join, and you'd have 10 electrons returning to the positive terminal. So as long as you think about it like that, it makes sense that those currents must be the same in each branch. To further illustrate it, which is just what I've been saying, but now using the conventional terms, the conventional current going clockwise in this case, and the amps as our measure of current rather than saying a number of electrons. If we have 3 amps of current in this circuit due to this battery, then there'll be 3 amps between the battery and the first split, between where it branches. And where it branches, you'll then get 1.5 currents going down one branch and 1.5 currents going down the other branch. The 2 branches in this case are identical, so we get the same current in each one. The 2 1.5 amp currents will then join back together and form a 3 amp current going back into the negative terminal. In reality, of course, it's the electrons going the other way, but it's still the same. It would be 3 amps worth of electrons, or negative 3 amps worth of electrons going along here, splitting into negative 1.5 that way, negative 1.5 that way, and joining back up into negative 3 back towards the battery. Right, so the same idea, but it's, as I said, if you understand where current is coming from, what causes it, what it means, and think about the number of electrons as being something that you can't just magically increase or decrease, it has to be electrons flowing, then hopefully this makes perfect sense. Voltage, on the other hand, voltage is still exactly the same as what we talked about for a series circuit. It is still the amount of that electric potential that each electron uses as it goes through the circuit. In this case, the electron will only go through one of the branches. So that means regardless of which branch it goes through, it has to use all 6 volts. And so it will spend it all on a single component. So in this case, the voltage across the components will both be 6 volts. Right? So the current is now half, but the voltage is the full voltage. Whereas in the series circuit, the voltage was shared because the electron could only spend half of its energy going through one component because it had to spend the other half going through the next one. Whereas here, each electron spends all its voltage going through one component, but it's only getting half as many electrons because remember, half the electrons will be going through the other component. The total voltage decrease across each parallel branch must be the same. If the electrons have 6 volts to spend when they arrive at this branch, when they arrive at the splitting, then they must have both spent the same amount, regardless of which path they go down, they must have spent the same amount when they rejoin. That may not look like it's too important in a circuit like this, but we'll get circuits where we have a parallel branch like this, but then another resistor between the negative terminal and the branch. And they'll have to spend some through these and some through that. And it'll become a bit more important when we look at circuits like that. So, solving circuit problems. We now understand parallel and series circuits. We understand all of the theory behind it. The last thing to do is to figure out how to actually get that information off a circuit diagram. And generally, when we're looking at a circuit diagram, we want to be able to find the equivalent total resistance, the total circuit current, and then the circuit current through each branch if there's a parallel section, and the voltage across each component in the circuit. So we basically want to look at a circuit diagram, and for any component, be able to say the voltage and the current through and across that component. You can then use the power formula, P equals VI, and calculate the power dissipated by each component and also by the whole circuit. So you should be able to do all of this for any circuit, and that's what we're going to do. We're going to work through that now. It is all on the screen right there, but I'm actually going to jump over to the document camera and do it on that as well, just to hopefully reinforce the approach that we use. So the, sorry, my camera's not quite lined up properly. Here we go. The simple first circuit that we've got is a battery going into a resistor, and then that's going into a light bulb, and then that going back into the negative terminal. We are told that this is a 6-volt battery. We are told it is a 5-ohm resistor, and we're told it is a 10-ohm light bulb. At this point, we can't immediately know what the current or the voltage across each component is. Actually, we could look at that and say, well, this is twice as big, so it'll need twice as much energy. So automatically, you should be able to look at that and go, well, this is going to have a 4-volt drop, and this is only going to have a 2-volt drop. But we can see that that'll come out of our formulas anyway. The first thing to do, actually, in any circuit analysis is to simplify it to the point where you've got a single component instead of however many you have. In this case, it's series. So we can simplify that by just going 5 ohms plus 10 ohms. Remember that series, we can just add it up. So our total is equal to 5 plus 10, which is 15 ohms. Right? And remember that that makes perfect sense, because an electron, if it's being opposed by 5 ohms and then opposed by 10 ohms, it's exactly the same as if it was being opposed by a 15 ohm resistor. So that means that this circuit is exactly the same as one like this. Right? I've switched now to a rectangular resistor, just to remind you that you can use any format, either form. So 6 volts and now 15 ohms. You'll see my ohms get messy sometimes. Doesn't matter. It's pretty obviously in ohms. It's certainly not a V or an I. So that's our simplified circuit. And the point of a simplified circuit is that we can now use Ohm's law. Right? We know V equals IR, or as I said the other way around, is I equals V over R, or of course R equals V over I. So those are all perfectly valid ways to write Ohm's law. But what they do is they allow us to look at the circuit. We know the voltage across the circuit. We know the resistance across the circuit, so the total resistance. And the only thing we don't know is the current, but now we can use our formula here to calculate that current. So we have Ohm's law will tell us that the current is 6 divided by 15, which is a current of 0.4. So we get 0.4 amps. And conventionally, that's going to be clockwise. Right? So the conventional current, that's going clockwise. In reality, of course, we remember that the electrons are going that way. They're going around anti-clockwise in this case. So we've got the current, resistance, and the voltage. That's great, but that doesn't really help us here. Right? What's our current and voltage across each component? It's great to know what the total circuit current and voltage is, but what about each component? Remember that for a series circuit, the total current is the same everywhere. If we have 0.4 amps worth of electrons leaving the negative terminal, if we have 0.4 amps leaving the negative terminal, then there must be 0.4 here, there must be 0.4 here, there must be 0.4 going through this, there must be 0.4 going this way through the resistor and then getting back to the positive terminal. So there must be 0.4 amps everywhere. So that means that the current through this resistor is 0.4 amps and the current through this light bulb is 0.4 amps. It is 0.4 amps everywhere, so the current through each component is 0.4 amps. And that's just telling us that the number of electrons passing every second is however many electrons we need to make 0.4 coulombs pass every second. And remember that an electron is negative 1.6, whatever it was, to the negative 19 coulombs. I think that's correct off the top of my head. So it would be however many electrons we need to make up that total number of coulombs every second passing through the light bulb and passing through the resistor. So that's cool. Now we know the current through each component is the same as the total circuit current. We know the total circuit voltage. The only thing we don't know is the voltage across each component. So how much voltage does it use going through the 5 ohm resistor and how much does it use going through the 10 ohm resistance light bulb? As I already mentioned, this one's twice as big, so we know it's going to be twice as much voltage drop. Hopefully, just automatically, you'll get to a point where you can look at the circuit and know that. But to start with, I don't expect you to be able to look at a circuit and just come up with those sorts of results, that bit of reasoning. What you can do instead is say, well, we know our current, and we know our resistance, and we know that voltage is equal to current times resistance. So we can go 0.4 times 10, and we get a voltage drop across the light bulb of 4 volts. And you could just say, well, it has to add up to 6, so 6 minus 4 is 2, or you could use the same formula and go 0.4 times 5 and check, yes, that is equal to 2. So we get a 2 volt drop across the resistor. And so now we know everything about the circuit. We know there's a 6 volt battery and that the electrons that come off that battery are using 4 volts to go through the light bulb and 2 volts to go through the resistor. The light bulb is 10 ohms, the resistor is 5 ohms. The current everywhere is 0.4 amps. That's all the information about that circuit that we could possibly need in terms of voltage, resistance, and current. What that then allows us to do, if we were so inclined, and we are going to be so inclined right now, is to figure out the power. I'm going to just get a new color for the power so I can just draw it on top of the same diagram. We're going to look at the power. So the power is equal to VI, and we have those bits of information. We have 4 volts and we have 0.4 amps. So 4 times 0.4, we have 1.6 watts. So if we have 0.4 amps of electrons, that's how many electrons are going past, right? However many electrons we need to go past to create a current of 0.4 coulombs every second. And every one of those electrons is using up 4 electric potential volts, right? 4 volts. Then that tells us exactly how much power is being used every second, and it is 1.6 watts, 1.6 joules per second. So that's exactly how much energy is being used in this circuit by all the electrons going through it as they go through that light bulb. And similarly with the light bulb, with the resistor, we have exactly the same idea, voltage times current. Now the voltage is only 2, but the current is still 0.4, so we have 0.8 watts, right? So 0.8 watts being used up here, 1.6 watts being used up in this light bulb, and that gives us a total power of 1.6 plus 0.8. So 2.4 watts. So our total power dissipation from the circuit, power dissipation just means how much is being converted from electric potential to other things, being dissipated, lost to the environment, because light and heat are just lost to the environment. So power dissipation of 2.4 watts for the total circuit. But the thing we can do to check, and I always recommend you do this, right? Always check, is that you know the total circuit current and you know the total circuit voltage, and you can just do a quick check that the total power is equal to the product of those. So 6 volts times 0.4 volts. With a simple circuit like this, it's pretty obvious that we've done it correctly, and we get 6 times 0.4 is 2.4 watts, and that's good, that agrees. So we can be happy with that. But as you get to slightly more complicated circuits, which we won't really do too much in this course, if you do continue to any other physics or indeed play with some electronics in your own time, then you may get more complicated circuits, and this check becomes more useful the more complicated the circuit is. For a fairly simple one like this, it's pretty obvious because we've got 4 volts and 2 volts, and both being 0.4 amps. That's going to be obviously the same as 6 volts times 0.4 amps. Excuse me. So that's the entire process for that first circuit, the series circuit. The next circuit we're going to look at is parallel. Again, there is a lecture slide with all of that information on it, but again, I'm going to do it manually so I can talk through it and hopefully help make it as clear as possible. So the circuit this time is almost the same. We've got 1 voltage source and we've got 2 items which convert energy into other forms. But this time, rather than a light bulb and resistor, it's 2 resistors, and this time they're in parallel. This time we have a 9-volt battery, not 6 volts, we're now 9 volts, and we have a 20 ohm resistor, 20 ohm, and a 30 ohm resistor. No, that's a bit awkward writing sideways, but there we go. 20 ohms and 30 ohms. Again, the process is the same. First thing we want to do is simplify it to be a single component, because a single component allows us to use Ohm's law to figure out the current through the whole circuit. And that's always a really good place to start. So we know the voltage is 9 volts. And so if we can figure out the total equivalent resistance and then get the total the total circuit current, that's a great place to start. So the parallel resistors means that 1 over R total is equal to 1 over R1 plus 1 over R2, which is equal to 1 over 20 plus 1 over 30. 1 over 20 plus 1 over 30 is equal to 1 over 12. You can use your calculators for that if you want, 1 over 12. So that means that 1 over R total is equal to 1 over 12, so R total must be equal to 12 ohms. There's our total circuit resistance, and that means that this circuit is equivalent to one that is just this, where we just have that, where we have 9 volts and 12 ohms. Now, again, just a reminder that this is a lower resistance than either of these, because each of these resistors is a pathway for electrons. And if you've got 2 pathways, then you're going to be letting through more electrons than if you just had one pathway. So we must have a total circuit resistance that's lower. So it's a good little sanity check. Obviously, we'll do our check at the end when we get to our power and everything, but it's a good little sanity check to make sure that if you've got two parallel resistors, that your final comes out less, right? The total comes out less than either of the resistors was. So 12 ohms makes sense looking at that. From that, we can then again use Ohm's law, which I'll write out all three again just for your use. Sorry, we'll need that one later, but that's the power one. V equals IR, I equals V over R, and R equals V over I. So there are your three Ohm's law formulas, and we'll just use those now. That's all we're going to be doing is applying those. We had a 9-volt battery and a 12 ohm resistor. So we want the current, which means we want voltage over resistance. So 9 divided by 12 is 0.75 amps. So we have a current around this circuit of 0.75 amps. And so in our theoretical single resistor, all 0.75 amps would be going through that resistor. But we don't have that here. We've got two different resistors. And that means that our 0.75 amps is going to be splitting up. We've got 0.75 amps here, but it's going to split up. And we're going to get some amount here and some amount here. And neither of them is going to be 0.75, but they're going to add to 0.75. And what we'll expect is, because this is the higher resistor, this will have a smaller one. So I'm just going to make a note to myself that this should be smaller and this should be larger. And that's another one of those little things that you can comment to yourself. You don't need to write it on like I have here, but it's a good little thing to comment to yourself so that when you get the values out in a moment, you can just double check with that and go, yep, it makes sense. It's what I expected it to be. And if it's not, then either your expectation was wrong and you should think about what the system is and whether you've got that back to front, or you should double check all your calculations, because it's quite easy to make mistakes as we work through. So where are we at? We've got our total circuit voltage is still there. We know the total circuit current, but we don't know exactly how it splits, and we know the resistance of each component. The other thing that we know is that because it's a parallel circuit, any electron that travels out of this negative terminal must use all its energy going through this one or through this one. It's not going to be part of it here and part of it here. It's only going to get to go through one, which means both of these have a 9-volt voltage drop. Right? There is a 9-volt voltage drop across either one, because the electron uses up all its energy going through whichever component it does go through. So both components have 9 volts across them. That means the electrons are using 9 volts as they go through them. That means that we can just use the same formula we did before and get our current the same way as we did for the total circuit current. Right? So we can just use that same formula. So we didn't even need to calculate the total circuit current to get this current through each component. But the reason we did is because it's a really good check to make sure those currents all match up. So what is the current? Our current through the first resistor, the 20 ohm one, is going to be voltage over resistance. So 9 divided by 20. And that gives us 0.45, right? So 0.45 amps here. And then we do the same thing, but over 30, and we get 0.3 amps through that resistor. And that means that we can see we've got 0.45 amps going this way, 0.3 amps going this way. The total is clearly 0.75, add them together, and that agrees with what we said before, 0.75 amps in the circuit as a whole. So that's great. We know the voltage, we know the current, and we know the resistance of every component, as well as the voltage and the current and the equivalent resistance of the whole circuit. So once we've done that, we're finished with our circuit analysis in terms of those three things. And all that's left is to go and calculate the power across, power dissipated by our circuit. And as we did before, we're going to do the power 3 times. We're going to do it for each component and for the total circuit. So the power of the 20 ohm resistor is equal to the voltage of the 20 ohm times the current of the 20 ohm, and that is 9 times 0.45, which is 4.05 watts. The power through the 30 ohm resistor, exactly the same, but now 0.3 amps, right? Same calculation, but with the current for that resistor gives us 2.7 watts, 2.7 watts, and the power through the total circuit is going to be the 9 volts, but times the total circuit current, which is 0.75, which gives us 6.75 watts. And you can check 4.05 plus 2.7 is 6.75. So that good, makes perfect sense. So, as we expected, the total circuit power is equal to the power down each branch. That is the end of the lesson. There is, I may as well show you the review slide just to be complete. There is all the stuff we've talked about, but that is the idea of this lesson, is the flow of charges and the circuits. And so sorry, I've just clicked the wrong button. The idea of being able to take a circuit diagram, simplify it, and work your way through finding the current, the voltage, and the resistance of each component, and therefore the current resistance and voltage for the whole circuit, and then the power through each component and through the whole circuit, all of that. That's the goal, being able to understand all of that. And the reason that I spent so long on the theory is that hopefully what you found when we were talking about the circuit is that you were still thinking about it all in terms of the number of electrons, the energy each electron is using, and it therefore made it a bit easier to understand why we use Ohm's law and why we have the current splitting the way it does and all of that kind of stuff. So that's my goal in my approach here. As I said, a lot of people teach this by just giving you the formulas. And they just say, if you've got series, add the resistors, then use Ohm's law, get the voltage, get the current, get the power, and just follow all the formulas and just do the maths and never actually think about the physics. And while that often does work, and you can analyze a wide range of circuits doing that, as soon as you get something that you get wrong, there's nothing in your brain that says, hold on, that should be different because I expected this behavior based on my physics knowledge. And so missing that means you're missing a whole critical step of your analysis of the system. And so I do prefer that you take my approach and think about that background to start with.